Hi, Charles. Okay, let's start. Okay, so we're on the topic of sensor data. Okay, so for data sensoring, the problem is different from the corner solution responses we had with the Tobit model. Okay. Okay, so the data sensoring arises because of the way the data are collected. Okay, so is the problem is not due to um, the behavior of the economic agents, but because of the way the data has been collected. Okay. So for example, for the Tobit model, if you're looking at, say, consumption of alcohol or cigarettes, there are some persons who do not um, consume alcohol or cigarettes. Therefore, you would expect a pileup of zeros for the left-hand side variable if you're looking at consumption. Okay. Okay, so um, okay, so we're shifting from the binary response models, where we have the basic models, the probit logic model, and then the corner solution models given by the Tobit models, into now methods for handling um, issues that arises because of the way the data has been collected. Okay. So for sensor data, we took binary sensoring and interval coding. Okay, let me go to the lecture notes. Um, okay, for binary sensoring, we have on the left-hand side a binary variable, uh, which is given here. W sub I is either 1 or 0, depending on this condition. And we end up with doing probit. So we end up doing probit of W sub I on Xi R sub I. Okay. 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 Um, though we do not directly get the beta coefficients, you have to um, use this to recover the beta coefficients, because after all, what we're interested in is these betas. Okay. So we can get the partial effects on the expected value of y given x. Okay. Okay. So you have to do this transformation. Okay. Okay. So after probe it, you still have to do this to get the beta hat chase. Okay. And then you have to, for test of hypothesis, then you have to get standard errors. You can obtain that either using the delta method or bootstrapping. Okay. Then we went to interval estimation. So now we have interval coded data where we have the left-hand side variable now defined as follows. Uh, the left-hand side variable is W. It ranges from 0 to J. Okay. Unlike the ordered probit model, we have the R's here are specified. Okay. And we end up for estimation, we have interval regression estimation. Okay. Then we have noted the differences between interval regression and ordered probit. Now, we move to the case of censoring from above and below. Okay. We'll discuss first censoring from above, and censoring from the analysis for censoring from below would just be analogous. Okay. So let us lay out the model. Okay. Consider now the case where the underlying variable y follows the classical linear model. Okay. So that is y is equal to x beta plus u. Okay. And the u's have a conditional distribution that is normal with mean zero and variance sigma square. Okay. But it is censored from above or right censored. So what we observe is W sub I, which is the minimum of y sub I or r sub I. Okay. So r sub I is the right censoring variable that may change with I, but sometimes it does not. Okay. So r sub I might be the same for all cross-section units, or it can vary across section unit. But then you have to specify it in your data set. Okay. So top coding is a common example of right censoring where, say, income or wealth is recorded up to a certain amount, and then we just know whether the value is above the amount. Okay. So for example, if R sub I is, let's say this is, we're looking at annual income. Suppose R sub I is 500,000. Okay. So that is the um, right censoring value, and suppose the actual income of the economic agent is 1 million pesos a year, then what would be recorded would be 500,000 instead of 1 million. Okay, because you take the minimum of Y sub I and R sub I. Okay. Another example of right censoring or top coding occurs with duration data. Okay. So note that in these examples, um, what we observe W sub I is comes about because of the way the data is recorded. Okay. And it W sub I does not arise because of a behavioral outcome. It's more of the way the data is collected or recorded. Left censoring or censoring from below occurs with minimum wages when we are interested in the value of marginal product. Well, in microeconomics, they say the wage um, the wage is the value of the marginal product. But then, if you have minimum wages, the minimum wage can be higher than the actual value of marginal product. But the observed wage would then be the minimum wage. Okay. Okay, we are interested in the features of the population distribution. As I mentioned before, d of y given x is the conditional distribution of y given x. Okay. So here we want the conditional distribution of y given x. Okay. Under the assumption that the expected value of u of x, u given x is equal to 0, that is, u is uncorrelated with x, that means we are primarily interested in the population regression function. The expected value of y given x is equal to x beta, which is completely characterized by beta. Okay. So given this model, since the conditional expectation of u given x is 0, then we have the expected value of y given x is equal to x beta. And this is what is of interest to us. So note that regression functions are couched in terms of model-wise as estimating this expected value. Okay? And in most cases, how you estimate this beta parameter is driven by the behavior of the disturbances or the use. Okay, so let's see how we estimate the case when we have top coding or we have censored from above or the data is right censored. Okay, so what we will be discussing is the parametric approach to estimating beta. That is in contrast to semi-parametric approaches that place fewer restrictions on this conditional distribution. So note that when we do maximum likelihood, we have to specify the form of the density function. Okay, that is the maximum likelihood estimation is an example of the parametric approach. Okay, so traditional parametric approaches specify the conditional distribution of y given x up to a finite set of unknown parameters and then use maximum likelihood estimation. Okay, so let's do that here. Okay, so with parametric approaches, we have to model the entire population distribution. the conditional distribution of y given x. Let us assume that the distribution of y sub I is continuous, so y has a density function. Okay, so let that conditional density function of y be denoted by this. Okay, so this is the conditional density of y given x and the parameter theta. So theta can be a vector of parameters. um, of course, in maximum likelihood, it is actually theta that we would like to estimate. Okay, and from data we can estimate the regression parameters of interest. Okay, so further assume that the conditional distribution of y given x sub I, r sub I is equal to the conditional distribution of y given x sub I. Okay, so what does this imply? So note that the right-hand side, r sub I disappears. Okay, okay. So that means that y sub I is independent of r sub I. Okay. I think we took this earlier. What you mean by this? Okay. So let us take two cases where W is less than R sub I. Okay, we're into the top coding case. So we have um, either W is less than R sub I, therefore the data would not be subject to coding. And the second case would be W is equal to R sub I. The recorded data is equal to R sub I. Okay, so that means that um, Y is top coded. Okay, okay. So if W sub I is less than R sub I, then we know that W sub I is equal to W sub I. Okay. If W sub I is equal to R sub I, then we know that W sub I is greater than or equal to R sub I. But what we observe is R sub I. Therefore, in that case, for that observation, the data is top coded. Okay, so we want to get this conditional distribution. Okay. So when the W is not subject to top coding, okay, so we have the probability that um, W sub I is less than equal to W given R sub I, X sub I, okay. But when is W sub I less than or equal to W, that is when Y sub I is less than or equal to W, okay. That is W is less than R sub I. So that is the case when W sub I is less than W, okay, given X, okay. And if you look at this expression, if you know the conditional density of Y sub I, that is the CDF evaluated at W conditional on X sub I and the parameters theta of this CDF. Okay. Okay. So this is the CDF of Y sub I conditional on X sub I. Okay. Therefore, the probability density of W sub I given X sub I, R sub I is simply, okay, this is the CDF. So just get the first derivative with respect to W, and you get the density function. Okay. Okay. So the probability density function of W sub I given X sub I, R sub I is the density, is this density function when W is less than R sub I. Okay, that is for values strictly less than the sensory point. Okay, when W is less than the sensory point. Okay, so now let us see if W is equal to R sub I. So the y sub I is either equal to the censoring value or greater than the censoring value. Okay, so that is the probability. So that event is when y sub I is greater than or equal to R sub I, conditional on X sub I, R sub I. Okay, so note that the complement of this is y sub I is less than R sub I. So this would be 1 minus the CDF evaluated at R sub I, conditional on X sub I data. Okay. So what is the probability density of W sub I? Okay. So note that W sub I, W can either be less than R sub I or W can be equal to R sub I. Okay. So the probability density of W would just be the product of these densities. So you would have either this or this. Okay. So you either have this when W is less than R sub I, or you have this when W is equal to R sub I. Okay, so for a particular observation, you would just pick up one of these factors. It's either you have this or you have this. Okay, so for the random draw I, if you take the log of this and have W sub I instead of W to denote that you have a particular observation W sub I, then you will get this expression. Okay, so that's just the log likelihood of this equation. Okay. Then you sum the expression across all I to obtain the log likelihood for the sample. Okay, so that's, you obtain the log likelihood, you maximize the log likelihood um, to obtain estimates of these parameters. Okay. In majority of the cases, the conditions sufficient for maximum likelihood estimation to be well behaved, well, the regularity conditions needed for maximum likelihood for the estimators to be consistent and square root asymptotically normal hold for censored estimation because the model this is smooth in theta. This continuous, this density function is smooth in theta. Okay. Okay. So interesting feature of the log likelihood. Okay. If we look at this, we only need to observe the censoring point R sub I for censored observations. Okay. We also need to know which observations are censored and which are not. Okay. This is useful for duration applications when the censoring value is reported only for observations that are actually censored. Okay. Okay. So far, we have just assumed some general form for this conditional distribution. Okay. Now, let's put in the assumptions for the classical linear regression model. Okay. So for the classical linear model, we have the conditional distribution of y given x is normal with mean x beta and variance sigma square. Okay, that arises because of the assumptions of the classical linear model. That is when you have the conditional distribution of u given x is normal with mean zero and variance sigma square. Then you can get the conditional distribution of y given x, and it would be normal with mean x beta and variance sigma square. Okay, so it is under this assumption that we obtain the censored normal regression. Okay, so that is where we get the censored normal regression. Okay, so that is where that normal term comes in. Okay. The censored normal regression model and the type 1 Tobit model serve different purposes. Okay, because for uh, the type 1 Tobit model that addresses the problem of corner solutions, while for the censored normal regression model that addresses the problem of data censoring. Okay, so those are two different problems. Okay, so if you look at the log likelihood for the censored normal regression model, then you would get this. Okay, so go back to this and then just substitute the normal density function here and then the normal CDF here. Okay, and you would get this. Okay, okay, so the econometric software do the censored normal regression estimation. For Stata, you have the command cnreg, okay, and it allows for both right and left censoring within the same data set. Okay. The approach for left censoring would just be analogous. Okay, so it's just the inequality signs that would change. Okay. So let's look at the difference between corner solution and censoring. An example would be the case of charitable contributions. Okay. So for charitable contributions, you can have both corner solutions and censoring. Okay. Suppose a survey records annual family charitable contributions. Up to 20,000, let's say a year, but the amount is top coded. Okay. Um, Actually, this example might be more relevant to the States because in the States, uh, charitable contributions can be tax deductible. So households might keep track of their charitable contributions for the year. Okay. The say for the survey, the charitable contributions are top coded at 20,000 a year. Okay. So even if you give more than 20,000, if you give 100,000 that year, what would be recorded would still be 20,000. Okay. Because you would get the minimum of 100,000 and 20,000. The minimum is 20,000. Okay. So the reported variable W, which is the minimum of Y, and 20,000 would clearly have a pile up at 20,000 due to top coding. Okay. It is proper to say that charitable contributions is censored from above at 20,000. Okay. It is not that you are copying actual charitable contributions, but the way you record the charitable contributions, it is censored from above at 20,000. Okay. So it is um, so the problem here is the way the data is recorded. Okay. At the other end, um, it's possible also that some fraction of the population would have zero charitable contributions. Okay, some might not be giving um, contributions to charity. Okay, an appropriate course of action then is to treat if there's a significant probability of observing these zero contributions, is to treat charitable contributions in the population as a corner solution with a corner at zero. Okay. So note that the observed zero arises not because of the way the data is recorded, but because that zero is actually a behavioral outcome. Okay. It's an outcome of consumer behavior. Okay. Unlike censoring from above at 20,000, it makes no sense to say charitable contributions is also censored from below at zero. Okay, there is a corner at zero, but it is not due to data censoring. Okay, so what do you do if you have both this corner solution at zero and data censoring from above at 20,000? Okay, then the estimation method that you can use is the two limit Tobit with limit 0 and 20,000. Okay, so this is the lower limit and this is the upper limit. However, partial effects are computed based on the standard type 1 Tobit model because we are interested in the conditional distribution of y given x, not the conditional distribution of w given x. Okay, so we're interested in this, the conditional distribution of y given x. That's why we're estimating these betas. Okay. Okay. Now let's have another example contribution to retirement plans. Suppose by law, individuals may contribute no more than 15% of their income to retirement plans. Okay. I think that holds, for example, for SSS, I don't know, for GSIS. Um, there's a cap on how much you would contribute. Okay. Okay. In the population, some individuals would contribute zero if they're not working. Then, um, or if they choose not to contribute to the retirement plan, to a retirement plan, they would contribute zero. Some will contribute at the upper 15% limit, and many will contribute a percentage strictly between 0 and 15. So in this case, you can again use a two limit Tobit. Okay. If we are interested in the effect of the explanatory variables on expected percentage contribution under the current legal regime, then we use the formulas for the two limit Tobit model. Okay. Okay. But sometimes you would see questions like, but what would be the effects of the covariates, the excess on the contribution percentage in the absence of institutional constraints. Okay. Okay. So here the left-hand side would be percentage of their income, okay, or contribution to retirement plans. Okay. Okay. Then we would be back to the previous situation. The corner at 0 is a corner that arises from utility maximization, but the corner at 15 is externally imposed. Then partial effects would be are computed based on the standard type 1 Tobit model. Okay. So note the difference in the question being addressed here, the partial effects under the current legal regime, or the partial effects in the absence of institutional constraints. Okay. You would use both two limit Tobit models, but for the interpretation, for the second case, you would revert to the type 1 Tobit model for interpretation. Okay. Any questions? So that is um, censoring from above and below. So for censoring from above and below, then we have the um, censored normal regression model. Okay, so here the lower limit and the upper limit are censoring values. Okay, for the examples, the charitable contributions and the contributions to retirement plans, we have slightly different problem. We have the case both of um, for charitable contributions, we have a corner solution at the bottom and top coding at the top. Okay. Okay. The same thing with retirement plans. Okay. So in these last two cases, you can use these examples. You can use the two limit Tobit model. Any questions? Okay. No questions. So that is data censoring. Okay. Binary censoring, interval censoring, and censoring from below and above. Okay. Uh, Binary censoring is not too common. Um, interval um, interval coding and censoring from above or below or and below um, is more common. Okay. So note that the methods we took address the data issues. Okay. Now we'll go to another set of data issues. And here we would have the sample selection problem. Okay. Okay. So let us go to the okay, so first we will define sample selection. Then we'll take the case when sample selection can be ignored. Then how do we remedy the estimation when there is sample selection? Okay. So here we have truncated regression the use of a Probit selection equation, the use of a Tobit selection equation. Okay, so these last three methods addresses the problem when you have sample selection based on the left-hand side variable. Okay, so first let's define sample selection. Okay, so the problem arises when we're using only a subset of the random sample obtained from a well-defined population of interest. Okay, so when you collect the data, you should define first your population of interest. Okay, so are you interested in, for example, you're looking at the Philippines, are you interested um, on inferences regarding all households in the Philippines, or are you interested only in, let's say, households in Metro Manila? Okay. Okay. So after you have defined that well-defined population of interest, most of our theory, where we get our traditional um, parameter estimates, uses a random sample from this population. Okay. The problem arises if you use only a subset of of a random sample. Okay. There cannot be an issue of non-random sample selection if a random sample has been obtained from a given population. Okay. So the population is not immutable. That means it is not some constant, though you define it at the start. Okay. We can choose a population of interest from a bigger population. So are you interested only for on children below 12 years old, or adults, or only the senior citizen um, population? Okay, so you have to define first your population of interest, and then sample from that population of interest. Okay. For example, if you are interested in the effect of a job training program on a population of men with poor labor market histories, we can define the population based on observed past labor market outcomes such as unemployment status or labor earnings. Okay, so here you have defined the population of interest to be first, you're interested only with males that have poor labor market histories. So you have to define what do you mean by poor labor market histories. So that can be maybe in terms of unemployment status in the past, or labor earnings. Okay. If we can collect a random sample from the defined population, we can just apply standard methods. Okay. We have no sample selection problem. Okay. Sample selection becomes an issue when the sample we can obtain is not representative of the population of interest. Okay. So that is basically what sample selection is. Um, that is, the sample obtained is not representative of the population of interest. Okay, let's have this example. Suppose you have the wealth equation, this wealth equation. Wealth is a function of plan, edu, age, and income. So here, plan is a binary indicator for eligibility in a pension plan, and edu and age are self-described characteristics of the household head. So edu can be measured maybe in terms of years of schooling, or you can have edu interval coded, okay? But you would sometimes see edu recorded as highest grade level attained, grade school, high school, zero education, grade school, high school, and so on. Okay, that does not come into our data censoring problem, because educ is a right-hand side variable. The interval coding problem we had before was in terms of interval coding of the left-hand side variable. Okay. Well, age is measured in years, and then we have household income for income. Okay. If we assume U has zero mean and is uncorrelated with each of the explanatory variable, we can use OLS if we have a random sample from the population. We have no problem. Okay. Suppose though that only people less than 65 years old were sampled. What if we use OLS on the selected sample? Okay. Note that OLS on the non-random sample in the sense that you limited the sample observations used in OLS to those where the household head had age less than 65. Okay. OLS on this non-random sample still consistently estimates the beta sub j, provided you still have this assumption, right? And the conditional mean is correctly specified for age less than 65. Okay. Therefore, if you get the expected value of wealth given this, then you have to specify age is less than 65. Okay. Okay. So it's like in the clinical trials for the COVID vaccines, initially Sinovac was not recommended for persons, for senior citizens 60 and above, because there were no sufficient trials for efficacy studies for those senior citizens. Okay, so they had discomfort in projecting the results of studies which involved persons less than 60 years old, and inferring from that what would be the outcome for those over those 60 years old and over. Okay, so this case falls under exogenous sampling. As you will see, sampling based on a response variable is much more serious than sampling based on an exogenous explanatory variable. This example, where you limited the sample to people less than 65 years old, is sampling based on an exogenous explanatory variable. If we are interested in the wealth function of all families, but we can obtain a random sample only for a subset of the population, then the restricted sampling raises a sample selection issue. Okay. Okay, but if the sampling is based on the exogenous explanatory variable, then you just have to be careful about interpreting the expected value of y given the excess. Okay, it's more problematic if you sample based on a response variable. Okay, so suppose, okay, so the next case is you a sample based on the response variable. Suppose that only families with wealth greater than zero are included in the sample. Now the data are selected on the basis of the response variable W, the left-hand side variable, using standard methods, including OLS on such a sample leads to biased and inconsistent estimates of beta J, even under the zero conditional mean assumption. Okay. Okay. So those are two cases of sample selection we have taken so far. Sampling based on exogenous explanatory variable, this first case, and then sampling based on a response variable. Okay. We'll take another case, the third case of incidental truncation. Okay. And this is where we would be using truncated regression and the selection equations. Okay. Um, okay. A different setup is when sample selection is not a deterministic function of either x sub j or y. X sub j is an explanatory variable, y is the response variable, but the sample selection may be related to these variables. This includes the problem of missing data, where data are missing or on one or more elements of this for some units drawn randomly from the population. This will become clearer when we go to truncated regression and the um, use of selection equations. Okay. Okay, for example, let y, the response variable, be observed only when a certain event is true. Okay, for example, let y be log of the offered wage. Okay, the log of the wage. So this is the log of the wage offer. That is the hourly wage someone could get paid if in the workforce. Okay. The wage offer equation is supposed to represent all people of working age, whether or not a person is actually working at the time of the survey. Okay. However, we observe the variable wage superscript O, the wage offer, only if the person decides to enter the workforce. That is, these wage data are available only for clearly defined subset of the population of interest. Okay. So if you are not working, then there would be no observed wage. Okay. This is a problem of incidental truncation. We only here we have self-selection. We only observe the wage offer if the person self-selects into the workforce. Okay. So whether we observe the wage offer depends on the outcome of another variable, that is labor force participation. Okay. So we must account for this non-random nature of the sample for estimating the wage offer equation. Okay. So you would also encounter this, for example, in the um, FIES or APS, these consumption survey data sets. You might be interested in health expenditure, um, but for some kinds of health expenditure, but you would observe zero health expenditure in some cases. Okay, if you are not, if no one gets sick, then it's possible that health expenditure is zero. Or also for educational expenditure, if you do not have kids in the household, or you are um, all working and not studying, then you might not have educational expenditure. Okay. So for incidental truncation, um, this is again a case where the left hand side variable is not always observed. Okay, the left hand side variable is observed only when a certain event is true. Okay, okay, so those are the three kinds of sample selection we're interested in. Sampling based on exogenous explanatory variable, which you would take in the next section, sampling based on a response variable, and incidental truncation. Okay. So let us see when sample selection can be ignored. We'll just do this for the linear model. That is, we have the form y is equal to x beta plus u. Okay. Um, Assume there is a population represented by the random vector x, y, z. Okay. So in our usual notation, x are the regressors in the right-hand side of the equation. Y is equal to x beta plus u. Y is the dependent variable. And z is a vector of instrumental variables. Because here in the model, we're assuming that some of the x's might potentially be endogenous. Okay. So here, x is a 1 by k vector of explanatory variables, y is a scalar response variable, z is a 1 by l vector of instrumental variables. So that just follows our usual notation. Okay. The standard linear model with possibly endogenous variables is this. Okay. Um, okay, so it's just a linear model, and we have the expected value of C transpose U is equal to 0. So that incorporates also X here being part of Z. Okay. No, not necessarily. It's just the uh, not necessarily. Okay. So we have X of 1 is equal to 1 to allow for an intercept. So we just have beta 1 here. Okay. So C sub 1 would then be also equal to 1. Okay. If Z is equal to X, the the instruments are also the explanatory variables. Then we're assuming that the explanatory variables are uncorrelated with the error. If Z is equal to X, then we have the expected value X transpose U is equal to 0. Okay, so given a random sample from the population, and suppose you have the rank condition, the rank of the expected value of C transpose X is equal to K, then we can just use two-stage least squares to consistently estimate beta. Okay. Okay, so we're here allowing for the possibility that some of the x's are endogenous. Okay. And if we do a random sample from the population, which we assumed before, then you can just do two-stage least squares. Okay. But what if you have a selected sample? Okay. Then the rank condition and this orthogonality condition are usually not enough to consistently estimate beta. Okay. Okay, so if you have sample selection, it does not always follow that two-stage least squares will give you consistent estimates. Okay, so let us see how that goes. Okay, so draw units randomly for the population. Okay, so for any random draw for unit I, suppose for unit I, we have x sub I, y sub I, and c sub I. Okay, then let us have a selection indicator S sub I. So that would be a binary variable. It is equal to 1 if unit I is used in the estimation, 0 if we do not use I in the observation I in the estimation. Okay. So S sub I indicates whether we observe all of X sub I, Y sub I, C sub I. So if we can observe X sub I, Y sub I, C sub I, we might as well include that in the estimation. Okay. So set sub I equal to 1 in that case. Okay. So the data you have would be this original variables plus the selection indicator. Okay. Where S sub I is either 0 or 1. Okay. So you have n observations in your sample. Okay. So for the population random variables, then you have X, Y, Z, and S. Okay. To determine the properties of any estimation procedure using the selected sample, we need to know the distribution of S and its dependence on X, Y, Z. So we would like to look at the relationship between the selection indicator and these variables. Okay. Okay. If S is independent of XYZ, the data are said to be missing completely at random. Okay. There would be where S is equal to 0, but the way you select um, the observations to include or exclude is random because under the assumption that S is independent of this. Okay, that intuitively makes sense. Okay, let's take the simpler case where L is equal to K. So the equation is just identified in the population. Okay, so let us look at the IV estimator using the selected sample. Okay, so this estimator is sometimes called the complete case estimator. So it's simply the instrumental variable estimator, but then you incorporate S sub I to pick up the observations that you are actually using in the estimation. Okay, so you would be picking up only the S sub i's where S sub I is equal to 0, is equal to 1. If S sub I is equal to 0, then it would not be included in this sum. Okay. Okay. So when would the IV estimator using the selected sample be consistent? Okay, that is the next question. Okay, so let's get the probability limit of beta hat sub IV. Okay, okay. So get the limit of this, get the probability limit of this. So the probability limit of beta, the probability limit of beta of the probability limit of beta is beta. The probability limit of this is the expected value of SC transpose X, then get the inverse, and the probability limit of this is this, okay? So note that if we have a random sample, the second term, this term would be 0, and we would get the um, instrumental variable estimator to be consistent, okay? So for consistency, we need to have this second term to be equal to 0, okay? So let us look at what conditions would ensure that the second term would be 0, okay? And these are the conditions, okay? The rank of C transpose X given S is equal to 1 is equal to K, okay? That just ensures that you can get this inverse, okay? And then the second condition is that this expected value of SC transpose U is equal to 0, okay? So that just makes sense, right? If this is 0, then, and this is defined, then the second term would be equal to 0, okay? Now for, in the general case, L is greater than equal to K. If L is equal to K, then the instrumental variable estimator is just the two-stage least squares estimator. If L is strictly greater than K, then you have to use two-stage least squares, okay? Now, what would be the sufficient conditions for consistency of the two-stage least squares estimator, okay? Then, following the results here, okay, then you would have this, okay? So these are the conditions when L is equal to K, and therefore you have beta hat instrumental variable. This is when L is equal to K, and therefore you have the two-stage least squares estimator, okay? Okay, so these are the sufficient conditions for consistency. So you have this. And for the rank conditions, then you have this, okay? So you have an added rank condition, the expected value of C transpose Z given S is equal to 1 is equal to L, okay? This is just for the feasibility also of the two-stage least squares estimator, okay? Okay, so these sufficient conditions ensure also that the two-stage least squares estimator using the selected sample is square root of n asymptotically normal, okay? Which is a nice property, okay? Now let's go back to the rank condition, these two rank conditions, okay? Practically, for the population to hold on the subpopulation, that is where S sub I is equal to 1. Okay, so this is where S sub I is equal to 1. We should have it holding in the population. The run conditions have to hold in the population, and the subpopulation must not be too small. Okay. How about for this first condition? When would that be? When would that hold? Okay, so we have these sufficient conditions for that condition to hold. Okay, we want sufficient conditions for this to hold, for this first equation to hold. Okay. Okay. So the sufficient conditions are S must be independent of ZU, and the expected value of C transpose U is equal to 0. So S does not depend on CU. S is independent of ZU, and the expected value of C transpose U is equal to 0. Okay. So let us show why you would get this. Actually, there should be no brackets. Okay. So let us get the expected value of SC transpose U. Okay. We said that S is independent of CU. Therefore, we can rewrite this expected value in this form. Okay. So the expected value of S times the expected value of C transpose U, because S and C and U, CU are independent. Okay. So let the expected value of S to be some value rho. Okay. So that is the mean of S, the mean of 0 ones between in the population. So that is actually the probability of an observation to be included in the estimation. Okay. But then we have the expected value of C transpose U is equal to 0. Therefore, we have rho times 0 is 0. Okay. Therefore, we satisfy this condition if this holds. Okay. So these conditions then imply the expected value of S C transpose U is equal to 0. Okay. Okay. If S is independent of X, Y, Z, the data are said to be missing completely at random. Okay. I mentioned that earlier, I think. Now let's look at another sufficient condition for this expectation to hold. Okay. Another sufficient condition is the conditional expectation of U given CS is equal to the conditional expectation of U given Z, and that is equal to 0. Okay. Okay. So if you look at the first equality, Okay, the first equality is this. The expected value of C given S is equal to the expected value of Z of U given C. Okay, so that rules out correlation between S and U. So note that S does not appear here anymore. Therefore, U and S are uncorrelated. Okay, so that's why you have here. Okay, now what would be a sufficient condition for S and U to be uncorrelated? Okay, the sufficient condition is this. The expected value of U given C is equal to 0, and S is a deterministic function of C. That is, S is a function of C, H of C. Okay, so let us show that. Suppose you have the expected value of U given Z and S, okay? So that is equal to the expected value of Z, but what is S? S is a function of Z, so you have H of Z. So you can write that as the expected value of U given Z, okay? Okay, but then we have the expected value of U given Z is 0, then that would be 0, okay? Okay, so these two conditions, imply this. Okay, okay. So note that S is a function of Z. Here you have S is a function of Z. And this is a case of exogenous sampling. Okay. The second equality is, I think, the second equality here. Okay, so this is the second equality. That is just an assumption on the exogeneity of the use of the Z's. Sorry. Okay. Now, what if C is equal to X? Okay, so this is a case where your instruments are X, so really you do not have an endogeneity problem with respect to X. Okay, so you can verify the sufficient condition is the expected value of Y conditional on X S is equal to the expected value of Y given X, and this is equal to X beta using the linear model. So this sufficient condition says that Y and S are independent, okay? And that S can be an arbitrary function of the exogenous variable X, okay? Then the rank condition is this. Here you're back to the OLS word. So you have this for feasibility of the estimator, okay? Therefore, if Y is equal to X beta plus U, and the expected value of X transpose U is equal to 0, we have the X's are exogenous, and S is independent of XY, then OLS using S sub I is equal to 1 is consistent for beta, okay? So that is for this special case. Okay. If you don't have the endogeneity problem and S is independent of XY, then you can use OLS on the selected sample and still get consistent beta hats. If we can obtain an equation where the selection indicator, so generally, if we can obtain an equation where the selection indicator is a function of the explanatory variables or instruments, we can apply OLS or two-stage least squares to the equation for consistent estimation. However, even with exogenous sampling, that is S sub I can be a function of the explanatory variables or instruments, we must use a conditional mean assumption in the underlying population. So when we interpret them, we have to take cognizance of our restricted sample. Okay. Okay. So that shows that when you sample based on the exogenous variable or the instruments, you can still do your usual OLS and um, two-stage least squares, but you have to be careful with the interpretation. You still get consistent estimates, but you have to interpret with care the conditional mean interpretation. Okay, I'll stop here and I'll continue with this application next meeting. Okay, so this is just a special case. And then we'll move on to truncated regression and the use of selection equations. Okay.
Ma'am,
Yeah.
question, ma'am.
Yeah.
So, what does it mean when a selection indicator is a function of explanatory variables or the instruments? So
So
does that
suppose,
mean
hmm,
that the selection indicator variable will characterize the instruments or the exogenous variables?
no, you just said, suppose you have your sampling, you're doing the regression only for households where the household head is less than 65 years old. Okay. So you set S sub I is equal to 1 if age is less than 65. S sub I is equal to 0 if age is greater than or equal to 65. Um, so for S sub I is equal to 1, those are only what you include in the regression. Okay, so note that for the beta hat IV, I have that S sub I there. So it only picks up those observations where S sub I is equal to 1, right? Uh, so it picks up only those household heads where age is less than 65. Does that make it clear? Okay. Yeah, but in our example, really worse in the what we had when we can ignore sample selection, we're really sampling based on the right hand side variables. Okay. Okay. So going back to that, so if you regress only on households with household heads whose age is less than 65, then um, you might not be able to infer regarding households whose household heads are have aged, let's say 80 and above, right? You do not know, you do not have information on those households. Okay. Well, that is the conditional mean. That is where the conditional mean thing occurs, right? Any any other question? Okay. So I'll meet you Tuesday, Thursday. Okay. I'll meet you this Thursday. So we'll move on to the remedies when the left hand side variable is the one that dictates the sampling. Okay. Okay. Charles, are you there?
Yes, ma'am.
Yeah. So you've given, I'll give them a problem set that covers probit, logit, tobit,
Yes, ma'am.
and the next problem set should cover.
Isa-send ko pa lang.
The next problem set should cover this sensor, this the sensor data methods.
Okay, ma'am.
Okay. And then the third should cover the sample selection methods. Okay.
Okay, ma'am.
Okay, so see you Thursday.
Thank you, ma'am.
Thank you po.
Max, you have a question?
Actually, question ko lang, ma'am. Like, in terms of the topics, after po ng sample selection, magano na po ba tayo yung mga special topics in times?
I'm still thinking if we have enough time for that. Kasi we just have 2 weeks left, diba?
Yeah.
So I'm thinking most like maybe not the macro part because that would require sort of a different framework.
Mm-hmm.
So I'll just choose a topic that more of an extension of this kind of data problems we have. So maybe I'll pick maybe
yung mga
topic
yes.
RDD.
Yes,
The RDD.
yes,
Yeah, the discontinuity.
regression discontinuity. Okay po.
It's just short and
Yeah.
more of an extension of the framework we're having.
Kasi I remembered po last time we also discussed average treatment effects, which is usually used sa mga difference in difference estimations.
Actually, difference is quite simple. So we can take it, but it's quite simple. Something you can study on your own. It's a lot less complicated than what we are taking in sample selection. So all these limited dependent variables, because you can just do OLS there. Well, I'll see then maybe difference in difference and the RDD. I do not want to go in depth with propensity scores. That would be a more extended discussion. Okay.
Yeah.
But if you need to do that, then you can handle that on your own.
Yeah. Okay na naman po yan. Sige pa.
So it's most likely RDD and maybe difference in difference. Okay.
Yeah. Naalala ko din po kasi ma'am kasi kay Professor Kraft po na-discuss po namin hanggang difference in difference. At least sa health po namin.
Yeah.
Pero yung RDD, di na po kami umabot dahil sa pandemic.
Yeah.
Nakat po yung class namin. So I think RDD would be nice din to focus.
So I'll put priority on RDD. Hindi ba simple lang yung difference in difference?
Medyo simple lang po siya. Pero hindi ko po siya na-appreciate before kasi di ko pa po alam yung fixed effects and yung mga random effects. Although, sa diba po may application din po na pwede mo pong extend yung fixed effects as difference in difference problems kapag panel data ang ginagamit.
Oo.
So, yun, parang hindi ko po siya na-appreciate on that level. Pero na-appreciate ko po yung interaction ng treatment and nung as the difference in difference estimator. Hanggang doon lang po yung level ng pagkaintindi ko at that time. Doon.
So I'll see between the two, but maybe I'll put priority on RDD because you can study difference in difference on your own, di ba? Okay.
Okay pa.
Sige.
Thank you po, ma'am.
Okay. So see you Thursday.
Okay pa. Bye pa.
Okay.
Thank you po.